Hi, welcome back. In the previous video, we looked at what neural networks are and how we can construct them. In this video, we'll talk about how to train them. Now, to start training a network, first of all, we need to design the network, which means we have to choose how many layers we have. We'll have to choose activation functions used in each layer. We can use sigmoids, but in fact, we'll see other functions which are much better for training neural networks. We'll have to then initialize the weights of every layer. You could initialize these just randomly, but we see that there are again other ways of doing that. There are some problems if you just do normal random initialization. After the data goes to layers, we get some predictions, and then we'll have a loss function like log loss that measures how good these predictions are given the ground truth, which gives us a loss, which we then give to an optimizer. Typically, this is a variant of stochastic gradient descent, which will then use this loss and then figure out how to update all these weights and all the layers so that the loss would be reduced, hopefully. And then we take a next batch of data, we feed it forward, and this circle keeps repeating over and over again until we see that the network doesn't learn anymore or starts overfitting. Right. So the algorithm behind all this is stochastic gradient descent, or more specifically, mini-batch stochastic gradient descent, right? Which means that we don't push all the data to the network at once, but we divide the data into smaller batches, and we push the data in batches one by one through the network. Why? Because that gives us enough signal to learn the weights, but it's much faster than giving the entire data set through the network. First of all, and second of all, we've seen in the first lecture already that stochastic gradient descent tends to converge faster than normal gradient descent. It's less affected by noise and so on. Right. So once we have our data batch, we push that to the network, and it is called a forward pass. Right? So we have some batch X, and we have many of these batches lined up, right? We push that through the network, and this is called the forward pass. And this is done very efficiently using some tensor operations. We'll typically be computing these layers in one go, one by one. Then we have the output y hat. We give that to a loss function together with the ground truth, and we'll get an error. And then we'll have a backwards pass, and in the backwards pass, all these connections, these weights, get updated. Right? So in the beginning, it was just random. In the next iteration, we'll change them a bit according to what would improve the loss. Right? So we'll compute the gradient of this loss with respect to all these weights in networks. Right? And this step is called backpropagation, which is an efficient way. There's multiple ways of updating the weights, but backpropagation is, for now, the best way we have to update all these weights efficiently. And you keep doing that. So you feed forward data, you update the weights. You feed forward data, update the weights. And so every time you update the weights until hopefully they will converge to a set of weights that is ideal and has very low loss. Hopefully low validation loss as well. Yeah. And the update basically consists of the previous weights. We do this per layer, right? So say we look at this layer here, the last layer, then we update these weights by taking the previous weight vector, and then we compute the gradient of the loss with respect to these weights times a learning rate eta, and we then update all the weights according to this gradient and this step size. We've seen this before, right? And then basically we do the same for the next layer and the next layer, the next layer. And then we do again a forward pass, we then update layer, 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 and so on. The forward pass is done efficiently using tensor operations. So a tensor, we've touched upon it before, a tensor is basically just an n-dimensional array. So it has a number of samples, and depending on your data, it can have multiple other dimensions. So if it's just a table-shaped data set, then we'll just have a 2D tensor. It will just have samples and features. If we have something like a time series, it's simply a 3D tensor. We'll have the samples here, we'll have the time steps here, and all the features, if you have like multiple time series, right, in this dimension. Yeah. And so every sample is basically a series in multiple features, and we have multiple of these. If you have an image, this is typically a 4D tensor because every image is one input. Every image has a height and a weight, and every image also has, typically is colored, so it has 3 channels for red, green, and blue. Right? So every image is then a 4D tensor. If you have a video, like every instance is a short sample of video, then you will have a 5D tensor because you also have the time steps as an extra dimension. So generally speaking, our input X is a tensor, and our weights are also a tensor, big W. Plus every node has a bias B. To compute the output of the first layer, so say we have a layer, input layer, and we have a hidden layer here. We have all the connections between these, which are our weights W. And this is my hidden layer here. To get the input for this node, or Z here, right? So Z is the input of a node. This is a vector. Don't forget that this is a vector, right? For all the nodes together. We take the dot product of one vector of our input X, right? So if we transpose a matrix, this is our mini batch. And this is one input. These are all different instances in our mini batch. And any instance has a number of features, and so these will be given to the inputs of our first layer. Or these are the inputs of our first layer. And then we take the dot product of these and the weight of all the connections of the first node here. That means we take this column here, right? This is all the values of our first example. We take the weights corresponding to one node, right? So if we have C nodes, we'll have C columns here. We have a weight vector for every node in the layer, and our data has B features and A examples. So the dot product of this one and all these layers here. So we take the dot product of this instance and the weights corresponding to one of these neurons, which gives us dot product. And this is basically inputs of our neuron plus the bias. Don't forget the bias. So that's the input of our neuron, and then we pass that through our sigmoid function, and that'll be the output of our layer. Now, because this is all vectorized, it means that we can just take the dot product of this matrix X times this matrix W, which gives us, say, a big, and we add to that the bias, and then this gives us our big value C plus the bias here. And this is then given as a matrix to the sigmoid, and the sigmoid then gives us a new matrix which has all the sigmoid values for every value in the matrix, and that's then the output of the first layer, right? And that's then the activation of the first layer, which you will then pass to the next layer. Okay. So basically what happens is if you have multiple layers, you input a tensor. After the next layer, you again have a tensor, and you kind of push these tensors through the network. And the efficient thing about this is that you don't have to do any for looping and so on. You just push the entire mini batch through the layer at once until you get the output Y. There are some element-wise operations as well, of course. The sigmoid just computes element-wise the sigmoid of every value in our matrix. And addition also adds here all the values of our matrix Z plus the bias in this case here. And this will again be a new matrix that we get out of it. Now, after we've passed the data through the network using these tensor operations, we get some output Y, or Y hat. And then we can compute the loss of this prediction with the actual true output Y. And now we want to use this loss to update the weights. So say that we have a hidden layer here, and we have, say, 2 output nodes. And so this gives us some predictions, Y, and then for that we compute the loss. Then we want to update this weight ij here. Or how can we change this weight so that the loss reduces? Now, purely naively, we could just like slightly increase that and decrease that and see which one is better and then use the best version of that, but that doesn't really work in practice. It's too expensive. So to optimally optimize this weight, we compute the gradient of this weight with respect to the loss function. Right, so we've seen this before with linear models. So if this is our loss curve, L, it's defined based on the activation function, everything else that comes into play. We'll get back to that. So the shape of this is not always convex. It depends on how the network is constructed. And so to find the optimal update for our first weight, we compute the gradient of this weight with respect to the loss. This tells us in which direction we need to update this weight. We then take a step using a learning rate, and this gives us our new, so this is n plus 1, our new weight. And we do this for all the weights in our final layer in this case. Okay. Now the tricky thing is, of course, that this is not a one-dimensional loss function. In fact, this can have thousands of dimensions, right? So we will update every weight according to what seems best for that weight, but in the meantime, all the other weights will also change. So what is the value of the next? What's the value of the loss for the next value W depends also how all the other values change, how all the other weights change. Right? So we have to compute this loss function, or we have to compute the gradient of the loss with respect to all the weights in the last layer. Right? So say that we have K classes, or K output nodes, and L hidden nodes. Then we'll have a K by L matrix, and so we have this matrix which has the gradients for all the weights in our final layer. Right? Then we compute this gradient for one input, x, small x, and we repeat that for every input in our mini batch. And we take the sum of all of these, right? So now this matrix has a sum of all of the losses for all the instances in our mini batch. After we have computed that, we can update the weights of a last layer using the update rule. Right? We take the previous weight vector minus the gradient, this is this matrix here, times the learning rate. Right? And so we update all of these weights simultaneously using this computed gradient matrix. After we've then done it for the last layer, we now do the same thing for the previous layer, and we iterate backwards through the layers. And we do this backwards because we've learned through experience this is much more efficient than doing it any other way. Now the process of updating all these weights is called backpropagation. And this can look quite daunting in the beginning, but it's actually quite intuitive. So let's just take it one step at a time. Let's start with a single data point A. Right, so we have all the values for A. We weight it by all the weights. We add a bias. We push it through our activation function. And so we can also represent this by g of z. And this is our output y for the last layer. Okay. Now we want to decrease loss by updating these weights. So say you have this weight W1 or W0. The same goes for the biases and the weights. But let's start with the weights, it's easier. So to update the weights, what we do is we now have to compute the gradient of the loss with respect to, so say you have y here, so we have the loss of y hat and y. Now we compute the gradient of the loss with respect to this weight here, W1. Now, we can't directly measure this because we have to go to these functions. First of all, the sum here, and then the activation function g. So that means that we have to apply the chain rule. Right? The chain rule says simply that if we have a function that's a function of other functions, it's basically just the derivative of the outer function times the derivative of the inner function. Okay? So in this case, this means that we first have to compute the derivative of the loss with respect to this activation g, right? So partial derivative of L according with respect to g. Then we'll have to compute the derivative of our activation function g with respect to the summation z here. Okay? And then we can compute the derivative of this function z, the summation function z, with respect to our weight W1. Right? Which means that our gradient of the loss with respect to our weight W1 here is the product of the gradient of the loss with respect to the activation function times the derivative of the activation function times the derivative of the sum with respect to W1. Now say that our loss function is, say, the regression, so we take the square loss as a loss function. Then the derivative of this according to g, and g occurs of course in this y. So we first have to take the derivative of the loss function, which the 2 goes here, right? So this becomes simply y minus y hat. Then we take the derivative of the loss function. So this will depend on which loss function you have. But you can typically look this up. We know the derivative of all the loss functions. And then derivative of this function z with respect to a. So say if you want to know this for W1, then this will be simply the value A1 over input x. So it's just the value of our input matrix corresponding to the weight that we want to update. Okay? So this is, for one layer, this is quite simple. It's simply a bit more complicated because we have these functions in between, but in the end this is very easy to calculate. Now we have this hidden layer in between. This complicates things a bit. So the idea is that next to updating these weights W1, so say that, to simplify, say that we find that, say the true value y1 is 5 and our y hat is 4, right? Which means that our output should be increased, it should be higher, right? Because it should be 5, right? So we want to increase the value for y. We can do this in two ways. We can either increase wy, right? So we compute the gradient what's the best increase of W1, what's the best change for W1, right? So this depends on what the input is. So if the input is positive, if A1 is positive, then you want to increase W1 so that Y also increases. If A1 here is negative, we want to decrease A1 so it becomes less negative. Right? So that's what a gradient does. The gradient computes how we should change W1 so that the loss reduces. Now, instead of changing W1, we can do another thing. We can change the activation A1 here. Now, we cannot directly affect A1. We have no control over that, but we do have control over all these weights. So the next question is, how can we change, what's the partial derivative basically of the loss function with respect to these guys here? If we can compute that, then we can also change A1 so that the loss again reduces. And that will be the next step. Right? So now we have our loss L, and we want to compute this with respect to this weight here, W01. Now, this means that we first of all have to compute the derivative of the loss with respect to A1. And then we compute derivative of A1 with respect to Z1, and then Z1 with respect to WZ1. Okay, so the derivative, so the gradient of the loss with respect to this weight here is the gradient of the loss with respect to this activation A times derivative of the activation function, right? So A with respect to Z. This will depend on what the activation function is used here in the hidden node, times the derivative of Z1 with respect to W. That will be again a lookup. Now we have these two are simple, so this is just a lookup. This we just have to see which is the input that we give to our data, the value in our inputs. The derivative of the activation function, again, we can look up. This is known. And the last one here, activation of the gradient of the loss with respect to our activation 1, that we will have to again decompose. So that will be the gradient of the loss with respect to our output G times derivative of G to Z, and then derivative of Z to A. Right, so derivative of loss versus G times derivative of Z versus the input Z here, and times the gradient of Z versus A1. Right, so you see that basically we went from before, where the loss was the sum of these three things. Now we replace this by these three things. And this can be repeated as much as you need. Right? So if you have to go even deeper, we again replace this guy with the three gradients of the previous layer. Right? So the gradient basically becomes a long product of all the different gradients along the way. How do we compute this guy here? Well, we already know this guy and this guy here, because from the previous step, right? It's the same ones as we had here. And then we still have derivative of Z versus A, and that's just looking up here what's the value that corresponds to A here. And then the derivative of A with respect to Z, this is a lookup again, depends on the activation function you have. It's just derivative of the activation function in the hidden layer. And then finally, derivative of Z with respect to W is just again as a lookup, and this will be the input X that we give it. So that's the whole thing for one data point and one output. Intuitively speaking, what we're basically doing is we're looking at if we have a loss, now how can we change this or this or this weight so that the loss decreases. Right? And we do that by, we decrease the loss by changing the weight of the final layer, and then we try to also improve desactivation A by updating the weights of the previous layer, and so on and so on and so on. Yeah. So also important to note is that since that every time we go deeper, it's again a product of three gradients here. This means that the gradient that we have here will get less and less powerful as we go through the layers. Right? If you're not careful, this gradient can quickly become zero. This is called the vanishing gradient problem. And so we'll come back to that, how we can avoid that. It's important to note. If you look at this, every one of these should not be near zero, otherwise our gradient will become zero and we cannot learn anymore. Once our gradient ends up being zero somewhere, our weights don't get updated and learning basically stops. Okay, so up till now we've learned how to update these weights so as to decrease the loss for one specific input and for one specific output. Now, if we want to do this for multiple outputs, we'll basically have to repeat this for every output. Basically, this means that if you want to compute the gradient with respect to A1, this is now not only affected by the output of this node, but also by any other node, because they all are affected by A1. Right? So now this term here is basically the sum of all the gradients for every output here. This is still for one input, so now we have to sum this up over all the inputs of a network. And if we have that, then we're done. Then we can update all the weights of the last layer by taking the previous weights times the gradient of the loss with respect to all the weights in the last layer, and then we do the same thing for the previous layer and the previous layer until we are at the input. So we're taking the loss and we're basically passing the gradient through the layers, each time updating all the weights until we end up with the input layer. Now, there's a nice video that I'll show you now, which kind of illustrates this whole process more visually. So just to explain this last point a bit better, this is from a tutorial by an excellent series of tutorials by Tree Blue and Brown. In this case, we explain here, well, they explain how backpropagation works. So say this is our last layer, and we have an output node here, and we want this to be 1, right? Because this corresponds to 2, and the input is a 2, so we want this one to be 1. We can use simple gradients to update all the weights so that it gets closer to 1. But now we also want to update all the activations of the previous layer. Right. So now we have to look, if this activation is positive, then we want to increase the activation. If the activation is negative, then we want to decrease the activation. So the activation here gets slower and this gets higher. And total, then this will become, this is the partial derivative for this activation. Right? This is the remaining gradient that remains after we have done the first pass. Now we can't change this gradient directly, the activation directly. We have to change the weights of the previous layer. So we'll compute basically the gradient that we have here. And we cannot do this for only one output, but we first have to look at all the other outputs as well, because they all have something to say about what the activation here should be. So basically we do this for all the outputs. So this is the gradient for this output, this is the gradient for the second output, and we sum it up over all the outputs, so we get the total gradient of the total loss for this specific input node here. So this will give us the final gradient that remains in this layer for this node, and this will then tell us how we should update the weights in the previous layer. Right. The important here is that this is the remaining gradient after it has gone through the first layer. And now we update all these weights. And the process repeats over and over and over again for every node in this layer. Now, this was just for one example. For this two here. So we learned all the updates of these weights. Now we have to do the same thing for all the other examples in our mini batch. So we compute all these new weights and then we sum them up. And this will then give us the new weights that we have to, well, this will give us the new gradients, and this will then give us the new weights for all the connections in our network. And if we do this now for all the 30,000 weights in our network, we get one new matrix, which is the gradient matrix. Right? So this is the matrix of all the gradients for all the weights. And this is what we then will use to update all the weights. So to summarize all of this one more time, a bit more formally, we can think of a neural network as a complex function, which at the end consists of an activation function A out. And the input of that function is, the dot product of the weights of the last layer times the output, the activation of the previous layer times plus bias. And the activation of this hidden layer is, again, the dot product of the weights times the input plus a bias, and then passed to the activation function of this hidden layer. Now, if we want to compute the gradients of the final loss with respect to these weights, we should first compute what is the remaining gradient of the loss after we end up in this node here. Okay. Once we know that, we only have to compute the derivative of this remaining gradient with the activation function and the activation function to the summation. And then we know this is exactly the value for W0. If you want to do the same here, it's this same gradient passed through this, well, multiplied by this, the derivative of this activation function, and then versus this one. And we do this for all the weights here. Now, how do we get this remaining gradient? That we can compute by looking at basically how this gradient goes through this network. So we look at the derivative of the gradient versus this activation function is 0, then derivative of the activation function versus the inputs, and then derivative of these inputs versus the specific weight that we want to change. And we do this for all the weights that affect this output A.